The Science of Motion, Stage 3, Laws, Principles and Concepts Related to Motion. Welcome to the virtual class of the Science of Motion. In this video, you will know the topics of Stage 3, which are gravitation, work, power, and energy. With focus on situations of daily life, will help us understand the planetary movement, the difference between work in physics and work as an economic activity, and the types of energy that bodies possess. Remember to have your calculator with you to solve the examples. We will start with gravitation from the point of view of Newtonian theory. To arrive at this theory, there was a series of previous antecedents and conceptions about the movement of the moon, the planets, and the sun, most of which were under the strong influence of Aristotle's ideas, who considered the Earth as the center of the universe, while the other celestial bodies revolved around her. It was Ptolemy in the 2nd century of our era who developed a system based on the Aristotelian conception to explain the planetary movement, known as the Geocentric theory of the universe, which mentioned that the Earth remained stationary in the center, while other planets, including the Moon and the Sun, went around it in circular orbits, and in turn epicyclical orbits, that is, describing the small circles around a larger circle whose center was the Earth. Later, in 16th century, Nicolaus Copernicus appears, and he proposed a different system, the heliocentric theory of the universe, in which he considered the Sun as the center of the planetary system, and the planets revolving in circular orbits around it, without casting aside the idea of the epicyclical movement of the other planets. Later, in 7th century, Kepler analyzed the observations provided by Braun and developed the 3 laws that describe the movement of the planets, called Kepler Laws. Then came Isaac Newton, in the same century, and took all the contributions of Copernicus, Galileo, and Kepler to combine everything in a complete theory, which gave origin to the famous Law of Universal Gravitation, which showed that all the bodies in the universe move under the same laws, no matter if it's here on Earth or in any other part of the universe. Let's go back to Kepler's laws. The first one mentioned that the planets move in orbits of elliptic form around the Sun, and the Sun is found at the focus of the ellipse. The second law said that the imaginary straight line that unites the planet with the Sun covers equal areas at intervals of equal times. And the third law mentioned that the squares of the orbital periods of the planets are proportional to the cubes of their average distance from the Sun. At that time, Newton related the movement of the falling of the apples with the movement of the moon around the Earth, and stated the law of universal gravitation in the following terms. Any 2 bodies attract one another with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. Developing the following formula, where F is the force measured in newtons, G is the gravitational constant with a value of 6.67 times 10 to minus 11 Newton square meter per kilogram squared, M represent the masses of the bodies measured in kilogram, and R the distance between them, measured in meters. In the following example, we will calculate the force of gravitational attraction between the Earth and the Moon. As data, we have the mass of the Earth, 6 times 10 to the 24 kilogram, the mass of the Moon, 7.4 times 10 to the 22 kilogram, and the distance between them, 3.88 times 10 to the 8 meters. Remember to add the value of the gravitational constant, and make sure that all the data is in the correct units. The next step is to apply the formula, and replace the data in this way. Use your calculator to do the corresponding operations. The force of gravitational attraction between the Earth and the Moon is 1.97 times 10 to the 20 Newton. Newton stated that the weight of a body on the surface of the Earth is equal to the force of attraction between the body and the Earth, from which the following formula arises, which substituting the mass of the Earth and the distance from the center to the surface of the Earth, giving us as a result 9.8 meters per second squared, a value known as the acceleration of gravity on Earth. In case of wanting to know the acceleration of gravity of a body far from the surface of a planet, the following formula is used, where r plus h represents the distance from the center of the planet plus the height at which the body is located. In the following example, we will calculate the acceleration of gravity acting on a body that is 1 million meters from the surface of Venus. As data, we have the gravitational constant, the mass of Venus, 4.88 times 10 to the 24 kilograms, its radius, 6.06 times 10 to the 6 meters, and the height of 1 million meters. The next step is to apply the formula and replace the data in this way. Use your calculator to do the corresponding operations. The acceleration of gravity at 1 million meters from the surface of Venus is 6.53 meters per second squared. In this part, I will show you how to use your calculator to solve gravitation problems, since many of the values are in scientific notation. For example, the gravitational constant. First, press the keys 6.67. Then, you will use the following key, which in some calculators can be found in this other way. Then, the minus sign, and finally, 11. Work is the scalar product of the magnitude of force F times the magnitude of the displacement x times the cosine of the angle theta that exists between the force and the displacement. The formula for calculating work is the following, where W represents work and is measured in joules. F is a force measured in Newton, x represents the displacement measured in meters, and theta the angle between them. When the force and displacement have the same direction, the work is greater than zero, resulting in an angle of 0 degrees. And by substituting in the formula, cosine of 0 is equal to 1. When force and displacement form a 90-degree angle, no work is performed, because cosine of 90 equals 0, and any multiplication by 0 results in 0. Power is defined as the amount of work performed in the unit of time, or well, the speed with which work is performed. The formula to calculate power is P equals W over T, where P represents the power in watts, W the work in joules, and T the time in seconds. Let's see the following example. A person pushes a 50-kilogram piece of furniture on the floor, displacing it a distance of 6 meters. If the force applied by the person is 600 Newton, letter A, calculate the work performed. And letter B, calculate the power if the work is performed in a lapse of 8 seconds. As the figure shows, the force and displacement form an angle of 0 degrees with the horizontal. In letter A, we need to calculate work. When we are substituting the data in the formula, we have 600 Newton times cosine of 0 times 6 meters. As cosine of 0 is 1, we can cancel it, because any multiplication by 1 keeps the same number. The work performed by the person is 3,600 joules. In letter B, we need to calculate power. When we are substituting the data in the formula, we have 3,600 joules over 8 seconds, resulting in 450 watts. Energy is defined as the capacity to perform work. There are diverse forms of energy. For example, when a fuel such as carbon is burned, it releases thermal energy. When we turn on a TV,
electric energy is used. When the human body digests foods, the chemical energy they contain is released. All bodies release radiation in function of their temperature. The sun, the stars, a light bulb, they are all release radiant energy. A nuclear reactor produces heat due to the release of energy of the nucleus of atoms. An object that falls freely possesses mechanical energy. When the word perform implies movement or the possibility of movement, we are talking about mechanical energy. Work can be considered as a change in kinetic energy of a body. This is known as the theorem of work and energy. Its formula is work is equal to final kinetic energy minus initial kinetic energy. The kinetic energy is represented by the letter K, defined as the energy a body possesses in virtue of its movement, and is calculated by the multiplying a half of a body mass by the speed squared. Work is also related to the change of position. This when raising a body to a certain height. Its formula is work is equal to final potential energy minus initial potential energy. The potential energy is defined as the energy that a body possesses in virtue of its position, and is calculated by the multiplying the mass by the gravity by the height at which the body was raised. As already mentioned, energy transforms when it manifests, but maintains the same amount of energy after transformation. This is known as the law of conservation of energy. Energy is neither created nor destroyed. It only changes form, but the quantity of total energy before the transformation is exactly equal to the quantity of total energy after the transformation. Applying this law to mechanical energy, we note that the initial mechanical energy is equal to the final mechanical energy, and that mechanical energy is the sum of potential energy and kinetic energy. Let's see the following example. A rock with a mass of 9 kg is in free fall from the top of a mountain. When it is at a height of 20 meters from the ground level, it has a velocity of 30 meters per second. Calculate letter A, potential energy, letter B, kinetic energy, and letter C, mechanical energy. In letter A, we need to find the potential energy. So, we need to substitute the data in the formula, then the potential energy is equal to 9 kg times 9.8 meters per second squared times 20 meters, giving us as a result of 1,764 joules. In letter B, we need to find the kinetic energy, so we need to substitute the data in the formula and multiply a half of a mass of 9 kg by the square of 30 meters per second, giving us as a result of 4,050 joules. In letter C, we need to find the mechanical energy of the rock in that position. We add the potential energy and the kinetic energy that we found in the previous letters, giving us as a result of 5,813 joules.
This would be all from Stage 3, where we saw the history of gravitation and the law of universal gravitation. Work as a product of a force by displacement and power as the speed with which work is performed. We also talk about energy, which is the capacity to perform work, the types of energy, and the law of conservation of energy. Remember to turn in your activities on time. See you!